So first of all, good evening, and I want to thank Barbara for having invited me to give this seminar today. These are the contents of this talk. I'm going to present some of the results of long-term research, because it started with me with my PhD in 2006. And during this period, I focus in particular on the teaching and learning of algebra. But today, the main focus of the talk will be on the research that enabled me to think about and introduce this construct. This is the acronym Model of Aware and Effective Attitudes and Behavior. So the talk will be divided into 4 parts. In the first part, I will introduce the research. Then I will move to an analysis of the processes developed by students when using algebraic language as a tool for proving. And then I will focus on the main focus, that is the role played by the teacher in supporting the students' development of all those competencies that are needed to use algebraic language as a thinking tool. And in the fourth and last part of the talk, I will present the use of this construct as a tool for pre-service teacher education, in particular in the context of university courses. So let's start from the first part of the talk. A premise is necessary, that is that the research that I developed was aimed at being a research for practice, since it is set within the Italian paradigm of research for innovation. Research for innovation aims at providing paradigmatic examples of possible improvements in mathematics teaching, at studying conditions under which these kind of improvements are possible and can be fostered, but also possible factors that could inhibit a good development of effective processes. And another important element is that the teachers are involved in all the phases of research, from the design to the implementation, to the analysis, to the reflection processes. And now I would like to introduce the educational aims, since it was a research for practice. And in order to stress on the need that suggested me to focus on these topics, I will read some sentences from the answers of a group of 9th grade students. They were at their first year of upper secondary school. And I'm going to read the answers to this questionnaire, in which we ask them to reflect on their vision of algebra. If you want to be rational, algebra is a bit pointless, because you don't need to add or multiply letters in everyday life. But we are in a scientific lyceum, so if I'm here, perhaps it is because I like it a little. Algebra is a method of reasoning used to develop the brain. In my opinion, it does not require memory, but constant exercise. In my opinion, during school time, it complicates problems, but prepares us to work and to problems of life. I don't think it is very difficult, because you just have to apply a few rules. I like it a lot, especially when I get the expressions. Algebra is beautiful, difficult, but I think you need arithmetic more, because in life you don't solve equations or factorize polynomials, etc. It's abstract, difficult, useless. So if I highlight some words in these sentences, we can see a widespread vision of algebra that emerges from the questionnaire. Algebra is useless. It is perceived as a senseless game. Success for most of the students is related to knowing rules and being able to apply them. And so most of them refers to the absolute power of memory. Those that write that algebra, according to them, is not useless, refer to it merely as an exercise for the mind, or, as I read in the second sentence, a game of complications, that is, a game that prepares students for the difficulty they will meet during their life. So the main idea is to try to overcome this widespread vision of algebra. But why this vision of algebra is so widespread? According to researchers that devoted research to these studies, and I'm mentioning two famous researchers, Kemp and Arkavi, the main problem is that in school there is a prevalence of approaches to the teaching of algebra that favor a development of instrumental understanding, that is, knowing rules, being able to apply rules, but without understanding the rationale behind them. And so, as Arkavi stressed, also those students that seem to be skilled in performing syntactic manipulations, transform, for example, expressions or solve equations very quickly, often they are not able to see algebra as a tool for understanding, expressing generalization, for reasoning in general. And so the aim of the research that I conducted in my PhD was to promote a different but appropriate vision of algebra. And when I use the word appropriate, I refer to students' idea of symbol sense, Arkavi's ideas of symbol sense. Symbol sense as being able to see symbols as bearers of meaning, knowing when to call on symbols in problem-solving processes, but also vice versa, when to turn to other ways of facing problems when they are more effective than using symbols. Appreciate the elegance, the communicative properties, the power of symbols in communicating, in solving problems, in supporting reasoning in general, and feeling the need to search for the meaning of symbols, whether it is essential for the solution of a problem or only when it serves to achieve new awareness about the problems that students are facing. How to promote this vision of algebra? There were, especially in the 19th, at the beginning of this century, a lot of studies on this issue. Alan Bell suggested to plan and design activities aimed at leading students through what he calls the essential algebraic cycle, that is, representing, manipulating, interpreting. Another important aspect, therefore, is to stimulate a conscious use of algebra as a language and as a tool for thinking. It can be done by devoting time not only to syntactical activity like what I said before, solving equations, simplify expressions, and so on, but also, as Kieran suggested, devoting time to activities that are not exclusively algebraic, but can be addressed in an effective way through the use of algebraic language. And Arkavi himself stressed that it is important to shift the focus from the problem of symbolic manipulation to activities that provide students with the opportunity of forget the rules and learn how to use symbols to think. And it was the aim of the educational project that I designed and implemented within my PhD. In particular, I focused on the design of a set of activities aimed at introducing students to the construction of proofs in arithmetic. Now I do not have time to show all the activities, but I want to share at least the structure of the educational path. It started with a phase characterized by activities of translation from verbal to algebraic language and vice versa. The second phase was focused on the interpretation of algebraic expression and in particular on the study of relationships between the properties of a given algebraic expression and the properties of the variables within this expression. The third and fourth phase are the central phases. In the third one, students were asked to analyze statements concerning properties of natural numbers and in particular to state the truthfulness or falseness of these statements and justify their answers. In the first phase, students explore the numerical situations. I will show in the following an example of problem from this phase. And they formulated the conjectures, and they were asked to try to justify this conjecture by constructing the proofs. The fifth phase was devoted to the analysis of proof strategies constructed by other students of other classes, for example. And the sixth phase was a phase of consolidation of all the competencies developed through the path, through the construction of proofs of assigned theorems. This path was experimented in teaching experiment that involved 4 different classes, 2 grade 10 classes, one from a linguistic lyceum and the other one from a humanistic lyceum, and 2 from grade 9 classes from a scientific lyceum. All these classes were in Italy. And in tune with Research for Innovation, also the 4 teachers were involved in the teaching experiments. Each class worked for about 25 hours. The methodologies, the activities. Students work individually only at the beginning and at the end of the path. Most of the activities were characterized by moments of small group work, followed by moments of classroom discussions on the products of the small group activities. So these were the main variables under research. Obviously, the mathematical content, in the case of my research, proved through algebraic language, the students, the teacher, and obviously all the interaction between them. I worked on different research questions. Today, I'm focusing on the 2 main ones. The first one is related to the ways in which students use algebraic language to prove statements involving numerical and arithmetical properties. And the aim of the research connected to this question was to highlight the key competencies that are needed for an effective use of algebra as a thinking tool, and also to investigate the interaction between these competencies. Then I turned to the interaction between the teacher and the students, in particular during classroom discussions, and I investigated the roles that characterize a profile of a teacher that is effective in guiding students to develop this kind of competencies. So let's start with the first research question, and so now I will focus on the ways in which students use algebraic language as a tool for constructing proofs. Before showing an examples, I will introduce the theoretical frameworks that I used for analyzing these thinking processes. The framework is constituted by 3 main elements. The first element comes from a model of teaching algebra as a game of interpretations introduced by Arzarello, Bazzini, and Chiappini. According to them, the power of algebra consists in the multiplicity of senses that are embedded in a formula or can be obtained by means of symbolic manipulations. And so they stressed on the key role played by conceptual frames. Conceptual frames are defined by them as organized sets of notions which suggest how to reason, how to manipulate formula, how to anticipate results when dealing with problems. They stress that reasoning through algebraic language is strictly related to the use of frames and to the capability of moving from one frame to another in order to interpret what is constructed through the manipulation of algebraic formula. Here there is the word anticipate. The second element of the framework is the concept of anticipating thought, introduced by Paolo Boero. Boero defines anticipation as the mental process through which one anticipates the final or intermediate form of an algebraic expression that could be most useful for solving a problem. And also the process through which one is able to anticipate also the direction of the transformation that are required to reach a specific form. Anticipation, according to Boero, and it is strictly related also to what Arzarello and colleagues says about an effective approach to the teaching of algebra. Anticipation is considered an essential element in the development of thinking when thinking is developed through processes of transformations of, especially of algebraic expressions. The third element of the framework is the idea of register of representation by Duval. Certainly it is a well-known construct. According to Duval, registers of representation are those semiotic systems that allow transformations of representation. In particular, he introduces two kinds of transformation: the treatments that are transformations carried out within one register, for example, when I solve an equation, and conversions that are transformations carried out between different registers. For example, when I draw a line starting from the equation of the line. So I made a conversion from the algebraic register to the graphic register. Duval stressed that the ability to switch from one register to another is a crucial aspect in the development of learning, since it allows to modify the transformations that can be performed on an object that is represented. During the teaching experiment, I collected all the written protocols produced by the groups of students during all the phases of the didactical path. And I audio recorded the discussions conducted by students working in small groups and transcribed them. And I analyzed both the written protocols and the transcripts of these discussions. And in particular, the focus of the analysis were these elements related to the framework that I've just introduced. That is the choice of conceptual frames that are used, that are activated by students to interpret or to transform expressions produced during the proof activity. And also looked at the coordination between different frames, the development of anticipating thoughts, and the conversions and treatments that are performed, in particular in relation to the coordination between verbal and algebraic registers. I'm going to present an example to show the kind of analysis that I performed. The example refers to this task from the fourth phase of the educational path. Let's read the task. Write a two-digit natural number and the number you obtain from it by inverting the digits. Determine the difference between these two numbers. Repeat the process from other two-digit numbers. What regularities can you observe? Can you prove what you claim? Obviously, there are different conjectures and explorations that can be done. Here I focus on the main conjecture. That is, all these differences are multiple of 9, and in particular, they are the product between 9 and the difference between the two digits. The proof, the algebraic proof of this conjecture can be easily developed by representing a two-digit number through the polynomial representation, that is, with this expression, 10m plus n, with this condition on n and m. And the number obtained by inverting the digits will be 10n plus m. So this is the difference between the two numbers. And this difference can be easily treated. So through easy treatments, we can reach this form that highlights that it's a multiple of 9 and it's the product between 9 and the difference between the digits. So let's see what happens within a group activity. This is the written protocol that was produced by the group. Some sentences are written in Italian, so I translated these sentences. We can see that the group wrote some examples. Then they tried to translate the number and the one obtained by inverting the digit in this way, but then they cancel this. They write they are all multiple of 9. Some condition on x and y, they write 10x plus y minus y plus x, they obtain 9x, and they write it is a multiple of 9. So we immediately recognize that there was a mistake in the translation. And yet we can see that to find the result of the difference, it is enough to subtract the 2/10 and to multiply the result by 9. So for example, here the 2/10 are 5 and 2. The subtraction between them is, the difference between them is 3. 3 multiplied by 9 is 27. So they, in the end, they write the, you can say, a complete conjecture. Let's see the discussion between them. At the beginning of the work, they construct some numerical examples and they conclude that the difference considered is always a multiple of 9. Then they decide to go on with the proof. And C says, let's do it with letters. This is much more complicated. It will be 10x plus y. And they write this on their sheet. Reversing it comes y plus 10x. So they only exchange the place of these two monomials. They write like this. Yes. And it comes, we have to make the difference. So we highlight immediately that while the interpretation of the term invert was obviously correct when they constructed numerical examples, in the phase in which they translated it into an algebraic expression, the conversion is not correct. And this is due to, in particular, to difficulties in the coordination between the positional notation frame and the polynomial notation frame, which is the one that is needed to be activated to perform correct conversions. And these difficulties have, as a result, a lack of internalization of the polynomial representation by the group of students. So she writes 10x plus y, we put it in brackets, minus y plus 10x, it becomes 10x plus y minus 10x. 0. In my opinion, something is wrong because it cancels. Does it become 10x plus 10x? They are cancelled. So they understand that there is a problem because they have examples, and in their example, they didn't find always 0. Meanwhile, let's write. And she dictates they are all multiples of 9. It's not easy. We can't prove it, it's difficult. We have 10x plus y, and that gives us a number. Then we have to do now, and Ego reads, inverting the digits. It's as if we have 1, and it's as if we take x this way, so we have to take y that way. But if we bring 10 this way, there's only be 1. So they understand that in the number obtained by inverting the digits, the digit that x, that was the 10 digits, will be the unit digit. So the coefficient will be 1 instead of 10. So it's no longer 10x, it's x in my opinion. Let's try. And C writes, so it would become 10x plus y minus y plus x. The y's cancel out, so they would leave 10x minus x, exactly 9x. We managed to prove it. We can see that the conversions activated is again erroneous. The processes, the interpretative processes that C activated to highlight the role played by X in the second expression to be written are not activated also to analyze the role of Y. And so they did not write 10Y. But then we observe another element in this phase of the process. That is, there is an anticipating thought that guides the work of the group. They want to prove that the form of the final expression is 9 multiplied by something. And so this anticipating thought predominates on other processes. In particular, it predominates on the control of what they are doing in algebra and on the interpretation of the final expression, which is not subjected to a careful interpretation. Then C looks at the numerical examples that they wrote on the sheet, and she says, but here I'm seeing something else, in my opinion, that practically this one is, look what I noticed. If you subtract the 2 tens, 8 minus 6, it's enough to multiply 9 for the subtraction of the 2 tens. 9 times 2 makes 18. So she made this observation and similar observation to the other 2 examples. We have to write this stuff down. I wouldn't have noticed. It's always a multiple of 9, and we can see that the result of the subtraction, just subtract the 2 tens and multiply the difference by 9. So we can observe that she focused on the expression 9x. She was not able to correctly interpret it, but this need of interpreting made her look at the examples, and she was able to find out another conjecture. So a more complete conjecture in relation to the one that they discovered at the beginning of their work. But if we see 9x in the examples, the number multiplied by 9 in the numerical example is the difference between the digits or the 2 tens of the numbers that are subtracted. So this sentence is correctly related to the numerical examples, but not to the algebraic expression. Here we can highlight an interpretative block related to this gap between the interpretation of numerical example and the interpretation of the algebraic expression that was produced during the group work. Do you know why it came to my mind? Because I saw 9x and I said, that's a multiple because there is x times 9. Then I said, but what is x? X is the 10. Then I tried to do x minus x. So again, also the classmates are really happy of these results and they say, brava. But again, we can see that there is a gap between, a further gap between the proposed algebraic representation, x minus x, and the verbal considerations, which are correct. If we go back to the example, to the proof of the main conjecture under scrutiny, we can highlight the key role played by different components in this process that seems to be very simple, but we saw from the discussion from the students, it's not so simple for them. First of all, there should be a correct activation of the polynomial notation frame to write this expression. the risk could be only to activate the positional notation frame. Some students wrote NM and then block. They were completely blocked. Then students should be able to coordinate effectively the frame polynomial notation with the frame positional notation. And we saw in this example that if there is not a good coordination between these two frames, it could happen that students, for example, translated inverting the digits as only changing the place of these two monomials. Then there is a need to refer to the frame multiple to activate the correct anticipating thought. That is, the final form of this expression should be 9 multiplied by something. And so this anticipating thought will guide the treatments to be performed. At the end, again, students should be able to coordinate the polynomial notation frame activated at the beginning with the multiple frame to reflect on the role played by the two digits, but M and N, in particular by their difference, in the results that are obtained. I analyzed a lot of discussions like the one that I showed, and it enabled me to highlight many sources of difficulties for students related to problems in activating all these components and of making these components interact effectively. First of all, I highlighted difficulties in coordinating different conceptual frames, and it is evident in the example that I showed. Lack of control in checking the correctness of conversions that are performed or in interpreting the meaning of expressions that are obtained through treatments. Also, this aspect is evident in the example that I showed you. Interpretative blocks, a lot of sources of interpretative blocks. Interpretative blocks associated with the activation of predominant anticipating thoughts, again, like in the example, but also sometimes associated with the absence of anticipating thoughts, activated with erroneous anticipating thoughts, or associated to difficulties in handling different conceptual frames together. So the difficulties faced by students in developing these proofs suggested me to shift the focus on the teacher's role and to try to find out if there could be a profile of teacher that is able to guide students to develop and to manage effectively the use of algebraic language to think. Again, I will briefly present the framework behind this construct and the introduction of this construct. The framework is a Vygotskian one. I refer to Vygotsky's ideas about the importance of social interaction in thought development processes and about the centrality of the contribution of an expert, an adult, or a peer in when students are in their zone of proximal development, so in bridging the gap between potential and actual mental development. I refer to Leontiev, in particular to his idea about the role that activities carried out in social contexts could play in fostering students' development of awareness of learning processes. Another element of the framework is the model of cognitive apprenticeship introduced by Collins, Brown, and Newman. They stress on the need of focusing on making thinking visible during classroom activities to bring light to cognitive and metacognitive processes that usually are not made explicit during mathematics lessons. This kind of approach is aimed at giving students the opportunity to observe, discover, invent the strategies developed by the expert in the very context in which they are activated. Finally, an important other source of reference is the idea of teaching as educating awareness introduced by John Mason, according to whom the task of teachers is to make students aware of concepts, techniques, heuristic strategies, and ways of thinking that enable students to make sense of mathematics. In this frame, the hypothesis that guided the analysis and the research was that the interplay between all the components that intervene in the development of thinking processes through the use of algebraic language, which is activated automatically by an expert, is not automatic by a novice. And so it's important that during the lessons, during the discussions, students, novices have the opportunity to see this interplay. So the teacher should make explicit and visible this interplay in order to enable students to internalize the necessary competencies needed and understand the meaning of what they are doing. And so the attitudes and the actions developed by the teachers plays a key role in guiding students toward the interiorization of all these aspects and in promoting the acquisition of these competencies. And in particular, I focused on the idea of teacher as a model. As I said before, we audio recorded the discussions developed by students in small groups, but I also audio recorded the discussions, the classroom discussions carried out by the teachers involved in the teaching experiments. I transcribed all the discussions, and so the data that were analyzed were the transcripts of classroom discussions, the transcripts of the activities of students working in a small group, and the path taken by the students, also the final reflections that each student wrote at the end of the teaching experiments, to highlight also possible links between the approach adopted by the teacher during classroom discussions and the students' approach when working in small groups or when individually, for example, facing the last test proposed to them at the end of the path. The construct, I already introduced the name of the construct. This is the acronym of teacher as a model of aware and effective attitudes and behaviors. The aim of the concept was to introduce the roles that the teacher activates to make thinking visible, to play the role of model for students, but also to support them in developing reflections at the metacognitive level, not only on the strategies carried out to solve problems during classroom activities, but also on the learning processes themselves. And I'm going to present these roles by analyzing an excerpt from a classroom discussion. This specific classroom discussion was conducted in a grade 9 class of a scientific lyceum. And the task under discussion is very simple. The class wants to justify that if B is an odd number, then 3B is odd. Obviously, this statement can be easily justified only verbally. I can say this is the product between 3, which is odd, and B, which is odd, and so the product between two odd numbers is again odd. Or we can use also mixed approaches with the use of both verbal and algebraic language. The aim of the teacher in this discussion is to focus on a complete only algebraic approach. Why only algebraic? Because this was a preparatory activity to the autonomous construction of proofs by the students. So the main aim of the activity was to make students realize the power of algebraic language as a tool for constructing reasoning. The algebraic approach is this one. At the beginning, the frame even odd should be activated to translate, to represent the fact that B is odd with this expression, 2n plus 1. Then a correct anticipating thought should be activated, that is that the final form of the expression should be 2 multiplied by something plus 1. Obviously, there is also a need of performing correct transformation at the syntactical level, but also of interpreting the algebraic expressions that are obtained during these transformations. So let's see what happened in the class. In the initial T is the teacher, and the students are represented with letters. At the beginning of the classroom discussion, the students agree that the hypothesis B is an odd number could be represented through this expression. So they already agreed this fact. Let's justify that if B is equal to 2x plus 1, then 3B is odd. We have to multiply 3 and 2x plus 1. The teacher writes it on the blackboard. 3 multiplied by, I write 2x plus 1 because I am assuming that B is odd. Then what can I do? And after this question, the class is silent. Can you see that it's odd? He's focusing on these expressions, indicating this expression. Yes, because there is a plus 1. Because there is a 1, where thou? In the parentheses. How can you show that a number is odd? You take a multiple of 2 and add it to 1. Here, can you see that it's a multiple of 2 added to 1? Yes, then it's multiplied by 3. Well, so far here, I only have a 3 times something. So she wants to stress that the main frame that is activated through this expression is the multiple one. We have 3 multiplied by something. But in the parentheses, yes. So let's see this part of the transcript. At the beginning, the teacher is playing the role of investigating subject and constituent part of the class. What is the idea of this role? This role is played when the aim of the teacher is to encourage students to take an inquiry approach and a collective approach to the resolution of problems. Usually the teacher uses in this case the first person plural because she's part of the group, so the we usually, not in this transcript, but often it happens. And to ensure that all pupils feel involved in the activity as a group, she accepts the different proposal without judging them. Then she focuses on the expression. Can you see that it's odd? How can you show that a number is odd? A lot of questions like this. And in this case, she plays the role of activator of interpretative processes and anticipating thoughts. These are two different roles. The role of activator of interpretative processes is played when the teacher stimulates the correct identification of the frames to which students have to refer in order to interpret an expression, a representation, or to transform a mathematical representation that has been constructed. This role is often played by asking questions aimed at clarifying the meanings of the representations that are constructed and at stimulating a continuous interpretation of these representations. And these are examples of questions that can be posed. The role of activator of anticipating thoughts is played when the teacher stimulates the activation of correct anticipating thoughts to predict the most effective approaches to deal with the problem. So, in order to activate this role, she proposed interventions aimed at focusing the attention of the students on the aims, on the objectives of the activity, or at exploring hypotheses and identifying the effects of a possible change or of a possible strategy that is activated. Let's go on with the discussion. The teacher says, inside the parentheses, it's true. Inside the parentheses, there's bound to be a not known. But what you told me is that I'd like to highlight multiple of 2 plus 1. Can you see here that I have a multiple of 2 plus 1? In round brackets, 3 times 2 plus 1. A is trying to suggest how to go on. What would you write? Dictate it to me, since I didn't quite understand. In brackets, 3 times 2 plus 1. And where do you put the x? Where do we put the x? 3 times 2x in brackets plus 1. Are these two expressions equivalent? A chorus of students answer no. Be careful then, because I have to make transformations that lead me to expressions that are equivalent to the starting one. You write 3 multiplied by, open square bracket, in parentheses, 2x plus 1. And the teacher writes this suggestion on the blackboard. Why to do that? It's the same thing. They are saying that, yes, the expressions are equivalent, but the students only suggested to have these 2 parentheses. So the frames that are activated are always the same. Let's remember what the goal is. I would like to highlight a plus 1, but in total. Here, a plus 1 is highlighted, but it's in the factor. So again, at the beginning, the teacher plays the role of activator of interpretative processes, like in the previous excerpts from this discussion, but also another role is played, the role of operative strategic guide. This is the role that is played when the teacher aims at sharing her thought processes, her reflections, the strategies that are activated. And so she asks questions or makes interventions to stimulate research into strategies or to clarify how an expert might pose herself or himself when analyzing such problem. Here again, the teachers play the role of investigating subject and constituent part of the class. She asks the students to dictate her. She writes also expressions that are not correct because she allows herself to be guided by the students and stimulates a collective approach to the problem. We observed in these excerpts 2 moments of block. The first one is or moments of difficulties. The first one is when A suggests to write the expression in this incorrect way. And in this case, the anticipating thought, I need the sum between an even number and 1, is predominating over the control of the correctness of the manipulations that are performed. And so A does not check this correctness. There was another moment of difficulties for students when S has lost sight of the goal, since now S has clear the anticipating thought, the need of working with equivalent expressions, but the anticipating thought in this case is inhibited. And so it suggests to make a transformation which is useless. In this interaction with these 2 students that face difficulties, the teacher plays another role, other two roles. The first one is activator of reflective attitudes and metacognitive acts. This role is played when the teacher stimulates and provokes meta-level attitudes, with an emphasis in particular on controlling the global sense of the processes. This kind of role is activated by asking questions aimed at helping students to identify, for example, strengths or weaknesses of particular strategies or arguments that are proposed, and to encourage an exchange between students, a comparison, a reflection on that can arise from this comparison. Another role that is played is the one of guiding, fostering a balance between the syntactical and the semantic level. This role is played when the teacher helps the students control the meaning and also the syntactic correctness of the expressions that are constructed and manipulated, but at the same time also the reasons for the correctness of the transformation they perform. She activates this role by making interventions aimed at getting students to reflect on the correctness of a certain transformation that is performed, or to make connection between, for example, the solution of a problem and the meanings behind these solutions. Let's read now the last part of this excerpt. The teacher says, this is what she said at the beginning, at the end of the other. Let's remember what the goal is. I would like to highlight a +1, but in total. Here a +1 is highlighted, but it's in the factor. And the student intervenes. She said, since you can do the calculations, you could do 6x + 3. Then it becomes 6x + 2 in parentheses, then +1. So N is really clear the goal of these transformations. Another student says, I get it. And the teacher, she says correctly, if I perform the calculations, I get 6x + 3. Then what is our goal? To bring out a +1, or rather to show that there is a +1. Now, can you see that it's an even +1? Yes. Or could something be done to make it even more evident? Pick up a 2. Let's do it. We have a 2 multiplied by 3x + 1 + 1. Look, we started with 3b and got 2 multiplied by something +1. As Em said, an even number +1 always gives an odd number. Here we can see when N displays this good semantic controlling and the manipulations and that she has in mind a clear anticipating thought that guides these manipulations, the teacher plays a new role, the last role that I'm going to present today, that is the role of reflective guide in the identification of effective practical strategic models. This role is really important because during classroom activities, obviously the teacher can play the role of model for students, but also peers can play this role. And so this role of reflective guide is played when the aim is to encourage students' reflections on the effectiveness of approaches that are proposed during classroom activities, so that students can identify such approaches as effective models from which to draw inspiration in tackling problems. And so she activates this role by making interventions aimed at helping students to make explicit the meaning of effective strategies of approaches. So, for example, the teachers ask, like in this case, the teachers reformulate, revoice what a student is saying in the lesson, or she asks to another student to reformulate what has been said during a lesson, or similar kind of interventions. In the last part of the discussion, the aim is to make the students reflect and control the whole process that was carried out, and so she plays again the role of activator of reflective attitudes. This construct is the result of the studies, the research developed during my PhD, but after the PhD, I used this construct in coordination with other theoretical frameworks to analyze the role played by the teacher in different situations, in stimulating generalization processes in the context of early algebra, in leading learners to develop argumentative skills, in activating formative assessment strategies, and also in guiding students in problem-solving activities focused on the construction and use of examples. And the construct proved to be a useful tool for highlighting effective dynamics, but also for highlighting those choices or those teaching approaches that are not so effective. And so it could represent a tool both to plan lessons and to a posteriori reflect on lessons, so on one's own practice. And this is why I had the idea to use this construct as a tool for teacher education. And I move to the last part of this seminar, the shorter one, since I'm not going to present analysis of data. And first of all, I want to present a model for pre-service teacher education, which has been adapted starting from a model for in-service education that I developed together with Nicolina Malara. The focus of the programs, of the activities designed for teacher education, in my case, was on the introduction of methodologies and theoretical constructs useful for supporting teachers in designing and implementing teaching activities. The background behind the program, the teacher education program that I'm carrying out with both in-service and pre-service teachers is constituted by Mason ideas about teaching, but also teaching education, teacher education as education to awareness. Here I quoted this sentence from this paper by John Mason, where he writes, educating teachers is about directing attention to practices and choices, constructs and theories, which can inform choices when teaching. And another important reference for my work with teacher is the research developed by Barbara Jaworski, in particular on the role that reflective practices play in fostering reflection about and comparison about teaching approaches and processes, and the importance of creating communities of inquiry in which a real sharing of practice and reflection on practice takes place. And so the aim of the program that I developed is to provoke in teachers shifts of attention that foster the development of awareness to guide their choices. This diagram summarizes a model for in-service mathematics teacher education that I designed with Nicolina Malara. The idea behind this model is that the observation and critical reflective study of classroom processes is a necessary condition for teachers to become more aware of different aspects, and that implemented this kind of reflection and the reflection on one's own practice with reference to specific theoretical lenses could foster the necessary shifts of attention that enable teachers to develop awareness about their practice. The program, the typical activities with in-service teachers that we carried out are characterized by 5 phases. The first 2 are within a moment which we called of study reflection. In the first phase, theoretical constructs and frameworks are introduced and studied. In the second phase, the teachers are asked to analyze the practice of others, for example, videos or transcripts from teaching experiments. Then there is a moment of action reflection. In the third phase, the teachers plan activities and implement them in their classes. In the first phase, they analyze the data from their teaching experiments, so they analyze their own practice. At the end of this process, there is a moment of shared reflection through a methodology that I have no time to present, a methodology of multi-commenting transcripts in which different teachers and researchers and teacher educators reflect on data collected by teachers in teaching experiment. And the construct of a model of aware and effective attitude and behaviors is one of the theoretical constructs that is shared during the first phase and is used during the other phases. In the case of pre-service teachers, it is necessary to introduce activities that enable them to imagine what could happen in the class, because at least in the Italian situation, in the first years of pre-service courses at the university for future teachers, teachers do not have field experience. So some of them never had the opportunity to be in a class as teachers or as observers. So there is need to make them imagine what could happen, first of all, in a real class. So this, the action, the phase of action, the phase of analysis of one's own practice, and this phase of analysis of data of actions from the teacher have to be substituted. And we substituted these phases with narrative activities, consisting in the creation of fictional classroom discussions in tune with the idea of lesson play. So phase 3 is only a phase of planning when, for example, they design tasks for students. Then there is a phase of creation of excerpts of classroom discussions and the sharing and comparison between the products of these phases 3 and 4. It is a cyclic process because these kind of activities are repeated several times, and obviously they alternate also with other types of laboratory activities for pre-service teachers. This is the structure. There is a task in which pre-service teachers are asked to create an extra-official classroom discussion, starting from a task for pupils and a selection of answers written by students, by real students during teaching experiment. And then they have to justify their experts and the choices they made, starting from this selection of answers, through an explicit reference to the MAEIB construct. In a subsequent phase, pre-service teachers are asked to peer review the product, that is the fictional, the excerpt from a fictional classroom discussion written by another group of placemates, and they have to refer to a grid of analysis that is provided to them. And then there is a moment of sharing and reflection during which the teacher educator design and orchestrate a collective discussion with pre-service teachers. With Francesca Morselli, with whom I'm working on these activities with pre-service teachers, we are developing different researches in these aspects, and we reporting into research report. the results of the investigation that we are doing of a per-service teacher's perspective on the use of this construct, of the MAAB construct, as a tool for education. In particular, during PME 2018, we presented a report focused on this kind of analysis. The participants to the study were 67 per-service teachers. They were enrolled in a mathematics education course to become primary school teachers. We in particular analyzed the reports that per-service teachers wrote at the end of the course. And the analysis was focused on different aspects, that is also on the awareness manifested by per-service teachers about the educational project within which they were involved. Here I will focus on the results related to the categories of reflections that per-service teachers proposed, and to the perspective adopted by them. We noticed that they adopted mainly two perspectives. One as students that have to carry out the task of creating a fictional classroom discussion. The other perspective is the one as per-service teachers that think as future teachers. Now I will be quicker because I'm taking more time than I expected. I want just to show very quickly the kind of reflections that the main themes that emerge from these categories of reflections. In relation to the activity of creation of fictional classroom discussion, when they speak as students that are performing a task, they share the difficulties they met. Difficulties in imagining pupils' intervention since they do not have field experience at disposal. Difficulties in creating efficient interventions of the teacher, but also in creating effective interactions alternating pupils and teachers' interventions. When they reflect on this activity adopting the perspective of a teacher, they reflect on the usefulness of this kind of activities for their professional development. And they stress that these activities represent an help to identify themselves with both the pupils and the teacher, and an help in understanding the work of the teacher and its complexity, and help a support in doing mental experiments of their future work, and a support in making them become aware of the competencies that they should improve in order to become good teachers. They also reflected about the role of theoretical constructs. In particular, MAEAB construct was the one that was used during all these kind of activities. When they speak as students, they stress that this tool represented for them a way to remedy to the lack of field experience, their lack of field experience. This tool is seen as a source of inspiration for designing activities and designing classroom discussions, and also as a support for the creation of this kind of discussions. And when they reflect as future teachers, they stress on the fact that this tool could provide guidelines for the teacher and could help understanding the complex work of the teacher and reflect on the responsibility that the teacher has. And I will end my presentation, my talk, reading an excerpt from the written report of a per-service teacher. I chose this excerpt since this per-service teacher is reflecting on the creation of fictional classroom discussion as a tool for her professional development, but also on the role of the MAEAB theoretical tool within this kind of activity. And she says, this activity leads one to hypothesize what might happen in the classroom and makes one think about how to orchestrate the discussion. This matters as long as it is not read as a rigid mental scheme, but is read as an experiment conducted in one's own head. Carrying out this activity is in itself a work on thinking skills, but secondly, constructing the fictional discussions leads to being able to see how each different type of question that one attributes to the teacher at a certain time causes different discussion scenarios to open up in the classroom. And with this, I thank you very much for your attention.